Hello, everyone. Thanks for being here with us today. We're really happy to have you join us for what should be an interesting and useful session. My name is Guillaume. I've been working at Craftform since 2008. I'll be your host for this webinar. I'm also joined today by my colleague Hugo, who is a senior FE engineer here at Craftform. Hugo brings a lot of experience in simulation analysis, and he will be sharing his experience with us during this session. Today, we're going to show you a very realistic simulation method. It helps us understand how the human body moves and reacts by using detailed digital models. Before we start, just a quick note. If you have any questions during the presentation, please type them into the Q&A box. We will answer them at the end. All right, let's jump in and get started with today's topic. So, what is Craftform? Craftform was founded in 2002 and started out offering reverse engineering and mechanical design services. In 2005, Craftform launched its own 3D scanning technology. Today, the company is one of the world leaders in 3D scanning and inspection technology, as well as in engineering service and software solution. In 2013, Craftform was acquired by Amtech Inc., a global company with over 150 offices in 31 countries and more than 21,000 employees. Amtech specializes in advanced electronic instrument and industrial technology. Being part of Amtech has helped Craftform grow and expand its innovation worldwide. Craftform now includes 4 complementary divisions to better meet the needs of its customer. The first one is Craftform Technology, Craftform Engineering, Crank Software, and Vertec. Now, let's take a closer look at Craftform Engineering, one of our key divisions. Craftform Engineering is made up of a multidisciplinary team of more than 150 experts. Our team includes specialists in mechanical, electrical, and software engineering, which allow us to take on a wide variety of projects. We offer a flexible service option to fit our clients' needs. These include the engineering on demand, where our experts support your team directly. The work package, where we take care of specific parts of the project. And the turnkey project, where we manage the entire project from the start to finish. Our team also has access to the best software tools in the industries, including suite from ANSYS, Dassault Systems, Siemens, and Autodesk. This helps us deliver high quality results no matter the challenge. Finally, Craftform Engineering is a security and confidentiality focused organization. We have the certification in place to meet strict industry standards, and we regularly work on highly sensitive projects that require advanced data protection and secure process. Craftform Engineering offers a complete and integrated approach to product and solution development built around 3 main pillars: design, engineering, and simulation. Our team brings strong expertise in industrial design, UX and UI, mechanical and electrical engineering, as well as in advanced simulation technology, such as FEA, CFD, and DEM. Thanks to this wide range of skills, we are able to support our client at every stage of their development. From the first idea to the final product, we help turn concept into innovative, high-performance solution. Now that you have a better idea of who we are and what we do, let's move on to the main topic of today's webinar. To guide us through this topic, I'm pleased to introduce my colleague, Hugo Bastien. Hugo, it's all yours.
Thanks, Guillaume, and thank you everyone for connecting today. I guess most of you are familiar with numerical simulation, but in any case, in a nutshell, numerical simulation encompasses a wide array of techniques of modeling and leverage a computer. When I say modeling today, I'm talking about representing a set of physics with mathematical equations. The two most popular techniques of numerical simulations are CFD, which stands for computational fluid dynamics, used typically to represent, for example, outside flows such as aerodynamics, or pump design or pump simulation, pump performance assessment, such as the one you can see here on top left of the screen. And you have also the other most popular technique, which is FEA, which stands for finite element analysis, typically used for stress analysis, displacement, vibration, and strain. You can see here, the bottom right of the screen, a classical thermoelastic distortion analysis carried on by FEA. And you have a specific subset of FEA, which is transient dynamic finite element analysis, such as the car crash you can see here, which is a scheme of computation which is more specialized to represent short time event with a lot of energy, a lot of non-linearities. Sorry. What are we going to talk about today? So today, as I said, we're going to talk about transient dynamic explicit analysis, explicit FEA. We're going to talk about human body modeling, of course, and we're going to talk about injury prediction. Before exploring the whole project, I want to tell you my 3 objectives for today, for this presentation. First, I want to demonstrate how numerical simulation can be leveraged to solve complex problems. Second, I want to show you how a team of numerical simulation experts can collaborate with your team of experts to achieve your goals. And finally, I want to show you through the slides how this kind of collaborations paid out with Lortie Aviation, our partner for today's project. Before going forward, a quick word about Lortie Aviation. Lortie Aviation operate a fleet of Hawker Hunters, so the plane you see here on the screen. They support training operation with the different armed forces since the year 2000s. They hired experienced NATO fighter pilots. They're based in Quebec City here, and they've been part of numerous exercises with the Army, Navy, Air Forces for the different countries in Canada, US, Europe, Far East, and Pacific theaters. Creaform Engineering and Lortie Aviation, it's a collaboration that dates from the year 2017. And one of the main projects we worked on since the beginning was the redesign of the main landing gear of the Hawker Hunter. Here you can see pictures of numerical scanning of the landing gear, testing of the landing gear, and finally numerical simulation FEA carried on the evolution of the design of the landing gear. The purpose of that project was to remove existing flaws of the design and optimize the design with today's technology. Over the years, a multiple team of Creaform Engineering has been part of the projects with Lortie in reverse engineering, mechanical design, electrical design, and of course, numerical simulation. Now about today's project. Today's project, the initial scope of work of the project was, is it possible to modify the seat in order to reduce the risk of vertebral injuries at the ejection for the pilots? This project have a lot of phases, but the three first phases was the main phases using numerical simulation. So we had the first phase, which was simply modeling, reproducing the ejections and understanding the kinematic of the ejections with a simple model. Then phase 2 was the introduction of a more bio-fidelic model that I'm going to present later on to represent the pilot, the anatomical structure of the pilot. And finally, the phase 3 was the assessment of the integration of the mitigation strategies suggested based on phase 1 and phase 2. The starting point of all this was the likelihood of vertebral injuries at the ejection. These planes are from the 50s, so these are quite old planes, but literature shows that predominance of vertebral fractures happens in the thoracolumbar region, so T11, T12, and L1, as shown here. And also, interestingly, literature shows that armed forces pilots are less likely to be injured than common people, either by their training, by their physical constitution, or by their skills, we might think. And why are we doing all this? Why are we trying to modify all seats to make them more safe or to prevent injuries? We have to understand here the context. We are dealing with aircrafts from the 50s. These aircraft are important assets for the training operations for the different forces to be able to complement their more actual assets. We have to understand also that the new Martin Baker seat, the new ejectable seats, are impossible to retrofit in these old planes because of the size, because of a lot of technical details. And we have to understand that we need to take action because there have been some reported cases of injuries for ejections happening. Now, the first phase of the project. As I said, the purpose of that first phase is to quickly represent the kinematics of the ejection, reproduce the ejection pulse, and understand how the loads are transferred and how the body reacts, so the accelerations of head, pelvis, and torso. First, what we did in phase one, we first digitized the seat and of course we used preform 3D scanners to do it. We built the first finite element model using a rigid body ATD, or anthropomorphic test device, in order to quickly have a model which can show us how the body reacts in the case of the ejection. So it allowed us to recover loads within the different body segments, and it allowed us also to recover peak acceleration impulses on head, torso, and pelvis. Here you can see on the screen the force pulse you have on the seat, creating the motion, creating the dynamic ejection. You can see here a photo of the seat design, the finite element model, and some pictures of the sequence of the ejection. What phase allowed us to do? Phase one allowed us to first engineer the foam of the seat. We ended up with viscoelastic foams in order to reduce at the maximum the impulse of the force impulse transferred to the pilot, and also reduce the maximum acceleration seen in the different body segments. Apart from the foam, the phase one allowed us to introduce a crushable layer. You can see here the final crushable and the test of the crushable we did. The purpose of introducing a crushable layer was to maximize the energy absorption in the design envelope that we had, in the space that we had. So with the FEA now, we were able to assess the effect of the design modification, so the addition of the crushable, the characterization of the foam, and the reduction of the size of the PSP because of the space we had. And we were able to simulate the ejection and get the reduction in acceleration and pulse based on caused by our design modification. So we are now at the end of phase one. We did reproduce the ejection with a quite simple model of the seat and of the body, and we were able, with the results of phase one, to already suggest some mitigation strategies in order to reduce the injury. So the addition of a highly viscoelastic foam, the addition of an aluminum honeycomb crushable layer, and what we know based on phase one, we know that we have a lot of energy to absorb, and we know that we don't have a lot of room in order to put some mitigation strategies. So with knowing all that, we go into phase two, where we try to introduce a bio-fidelic model in order to more closely represent the injury itself, understand how the body reacts, how the anatomical structure behaves. So we opted for the TUMS, the Total Human Model for Safety, developed by Toyota and made public a few years ago. Why did we use such a model? We wanted to leverage an existing model, which is quite defined in terms of anatomical structures, and we wanted also to try as quickly as possible reproduce the injury and recommend mitigation strategies. So by leveraging that kind of FEM, we saved a lot of time and effort. We knew in advance that we were going to deal with some uncertainties, for example, in the material properties, because these material properties have been correlated for another environment, which is the car crash. And we also knew that we needed to position the model differently, which was challenged to keep the representativeness of the model. And by the way, positioning the model was a real challenge because we wanted to preserve the anatomical accuracy of the model, and it was not a small task. Let's just say that. Here you can see we integrated the TUMS in the ejection simulations. So you can see here the behavior of the spine, which is something we expected, but it's impressive just to see it. So as you could see, the spine in the previous simulation, the spine see a lot of strain. So the vertebra see a lot of compression, and you can see here on the graph the measurements of the anterior eye compression that we predicted by the simulation on the different vertebrae. And you can see that T11 and T12 are seeing a great deal of compression more than the other vertebrae. That was to be expected based on literature. We discussed the injuries a few slides ago. So that was to be expected, but the simulations showed us that the rib cage is rolling forward. So the rib cage is rolling forward, creating an hinge-like phenomenon at the base of the rib cage, which is less stiff. And that explains why T11 and T12 see a great deal of compression. Here after seeing all this, we wondered, is it possible to reduce the compression of the vertebrae by adding some kind of pretension in the belts? And when I'm talking about pretension, I'm not talking about just tightening the harness or the straps by hand, but I'm talking more about including a device which will retract the belt to ensure that the posture of the pilot remain with all the loads, all the G's seen by the body will remain upright and will not roll forward like this. So we introduce forces of pretension in the belt, such as the one created by belt retractors that you can see in automotive industry. And we first used arbitrary load values because we don't really know what the loads are going to be, but it was just to see if it was theoretically possible to restrain the motion of the rib cage, to restrain the compression of the vertebrae, and to restrain the curvature and to reduce the curvature of the spine, such as the one you can see here. And you have the comparison between the two. So we end up using 2 kilonewton in the straps and showing that yes, it's theoretically possible to reduce the vertebra compression. And within this simulation, we've really focused on T11 and T12, the vertebrae you have here, to see what if our pretension was having the effect we want, so reducing the EA compression on these two vertebrae. Showing with some numbers, here you can see on the different, on four of the vertebrae, T10, T11, and T12, and the L1, sorry, and L1, the thoracolumbar region, you can see the reduction of the strain of the anterior head compression. So you can see that specifically for T12 and L1, the reduction in compression is significant. Almost 80% of the compression is prevented by just having the belt retracted and the body remaining upright. Here on the graph, the y-axis is representing the anterior 8 compression, so the compression of the original 8 in absolute value, and you can see that out of the, for example, for L1, out of the 5%, we remove 3.5% of the compression, so it's quite significant for such the reduction. Now we wondered. We use 2 kilonewton of pretension load. What if we use different load values because we don't know the exact value we're going to get from the belt retractors? And we conducted sensitivity studies on the belt pretension loads, and we saw that for some of the vertebrae, the reduction in compression is quite proportional to the load we use, and for other vertebrae such as T12 and L1, only having some pretension, here without pretension and here with pretension, only having some pretension keep the body upright and prevent all the compression we add in the original simulation. So that was interesting because we knew that only with pretension, no matter what the final load value was, it's possible to have a positive effect on the vertebra compression. And also, since the beginning, we were using a single version of the thumbs, a single size for the pilot. So we wondered, okay, what if we change the size of the pilot? What if we change the setup of the harness, the setup of the webbing? And we conducted some sensitivity analysis on the size of the pilot with the available models. And we also positioned the harness differently at different angles to see how the performance of our solutions and the performance of the reduction was impacted by these different configurations. We saw, of course, that there is some effect if you change the size of the pilot, if you change the configuration of the harness, you have some impact on the magnitude of the improvement, but nevertheless, you have a positive impact on vertebra compression, and that gives our solution more robustness to know the results of these sensitivity studies. Now, the logical next step was to carry down some physical tests with actual belt retractors. So we did a test setup using a Martin Baker seat, belt retractors, dummy, an ATD, a physical ATD, and we measured the loads and the displacement that these belt retractors, commercial in the automotive industry, were giving in order to make our simulations more realistic or more physical, let's say. And we had quite a surprise. We had the surprise to see that the loads applied by the belt retractors were at risk of creating collarbone or clavicle fractures in the pilot. And at first we said, okay, if we save the vertebrae from the compression and we have only collarbone fracture, that might be less severe or less important, but it's not an option because the pilots sometimes eject into the ocean and they need still to be able to swim and to climb on their raft. So it was the risk on the clavicle fracture was still unacceptable. So where we are right now, we just ended the phase 2. We introduced a more bio-fidelic finite element model, the TOMS. We saw with the new simulations that the posture of the pilot at the ejection is really important. And in order to have a better posture, maintain posture, we added some belt retractors, and we simulated and we measured the effect of the belt retention on the risk of fracture. So we are diving in phase 3. And we have two goals in phase 3. We have to integrate the belt retractor within the design, and there are a few steps we need to do in order to do that. And we still need to deal with the collarbone issue because it's still unacceptable. We need to find a solution to that problem. In order to work on this, the last thing I mentioned, the risk of collarbone fractures, we partnered with TopMed. TopMed is a center for R&D for orthotics and medical equipment specialized in biomechanics, based here in Quebec. So we worked with them in order to design an orthosis, in order to distribute the load on the muscles, so on the muscles on both sides of the clavicle, in order to reduce the loads applied on the clavicle. So they helped us in order to do that, to introduce an orthosis. So they designed an orthosis which consists of a pouch. Here you can see the pouch filled with air cells, and the pouch with the air cells ensure that the load is distributed on the muscle groups, so not only on the clavicle. And they also developed an instrumented torso in order for us to be able to measure the impact of the addition of the orthosis. So they helped us develop the mitigation solution, the mitigation strategy, which is the orthosis, but also the test device we needed in order to validate its performance. So with all that, we carried on some belt retractor and orthosis physical tests. So we did some tests with the seat, the belt retractors, the instrumented torso, and the orthosis. You can see here the setup in different angles. So you have the retractor here, you have the belt, you have the instrumented torso in this, and we don't see it that well, but you have the orthosis in the mix. So the goal was to assess the effect with and without the orthosis, and to quantify the likelihood of the fracture with or without the orthosis. What we saw that, for example, the red curve, you have the time scale is not that important here because we're talking about a pulse of the retraction, but putting them all on the same time scale, we can see the different tests here. You can see in red the test without the orthosis, and we can see that the loads on the clavicle, because you have the instrumented clavicle in the device measuring the loads applied on it, you can see that the load on the clavicle is exceeding 3.5 kilonewton. So you can see that the sensor here is saturated. So the loads for all the tests carried was above 3.5 kilonewton. And you can see, surprisingly, with the orthosis, the three tests here, you can see that three tests demonstrated loads below 0.5 kilonewton. That is huge, because the literature tell us that you have to be worried about clavicle fracture at about 1 kilonewton. So we pass from above 3.5 kilonewton to below 0.5 kilonewton, which was really encouraging for us. So we have a mitigation for the mitigation. We have a mitigation for the risk of the clavicle fractures, but we still need to find a way to activate the belt retractor. So one problem solved, and let's work on the other one. So at that point, we needed to design a trigger in order to activate the belt retractors, because they're not to be activated by hand. We don't want you to have to do something or anything. So we have to find for the belt retractors to design the pulse requirement. We needed the electrical pulse we needed to activate them. We needed to design the pulse generator itself, so the 3D design, the geometry, and all this. And we also needed to make sure that the design was reliable, redundant enough in order to prevent the belt retractor to be inactive. And we needed to ensure that activation occurs at all times. So here you can see the final design on the screen here. And we also finally, I didn't mention it, but we needed to integrate that trigger into the cockpit and make sure that everything was feasible. Here are quick electrical schematics of the solution. So you can see we have some spring-loaded dynamos here. We have batteries. So we have two different technologies activating the belt retractors, and it ensures us that we are immune to some problems, because both technology won't be inactivated, if I can say, by the same problems. It ensures us robustness and redundancy, principally. So that was the goal of having two different technologies, and it was really to be sure that activation was possible at all times. Finally, another thing we had to be worried about was not worry about, but carry was the integration in the cockpit. So you can see here that the belt retractors are integrated to the seat, directly on the seat. You can see that the trigger is integrated on the bulkhead behind the seat. And I show you the battery pack here. The battery pack is not integrated directly on the side of the trigger, because we want the battery pack to be isolated in order not to be affected if, for example, something is close to it. So we put the battery pack in the avionic bay to be not in the same area as the other items. So we are more maybe immune to some regions' problems. Finally, with that solutions, we want to ensure robustness. So we established a detailed technical specification based on the design requirement, of course, but also based on environmental requirements, such as the acceleration levels, the temperature levels, and all that. And we inspired from the ISO standard. We devised the different validation methods that we wanted to test or to validate, in order to make sure that every functional requirements from both design and environmental were satisfied. So if I summarize what we did and what I discussed today, the initial scope of work was to modify the seat to reduce the risk of vertebral fracture during the ejection. We first went with three phases. So the first phase was to quickly reproduce the kinematics of the ejection, and it allowed us to integrate the few mitigation strategies, so the engineering of the foam, the integration of the crushable layer, and it allowed us to dive into phase two, where we integrated a more bio-fidelic finite element model to more closely represent the injury itself. And we saw with the simulations on phase two that we couldn't saw with phase one, that the posture was really important. The maintained posture of the pilot at the ejection was the key in all that. And finally, in phase three, we used the FEA, finite element analysis, to make sure that we were integrating mitigation strategies that were efficient, and that allowed us to realize some other risk, for example, for the collarbone fractures, and that allowed us to make more robust final solution. Right now, we are in the test phase, so phase 4 to 8, which ensure that the solution is robust and the solution is proof tested, and the final validation is gonna come shortly for this system, and it's gonna be integrated in the hot routers, hopefully. Now, with this presentation today, I hope I showed that numerical simulation can be used to understand complex problems, to optimize the solutions to these same problems, and to reduce any risk associated with it. And in this case, we have to understand that numerical simulation is the key, since we cannot test on a real human body. So the numerical simulation, the explicit transient FEA that we did, allowed us to test on virtual human body. So virtual test on human body, and to be able to measure within an anatomical structure, which is hardly possible with live human subjects. So I also hope I showed you that there's a real benefit of hiring an expert team in numerical simulation for your project. So these experts are specialized. They are available sporadically if you need them sporadically, if you don't need them full time. They have some cutting edge expertise that you can rely on. And also, interestingly, when we come to work on a new project, we have an external perspective, and that can be really powerful to add to your team. We know that you are an expert on your product, but we are expert on the technique, so that's complementary, if I can say it that way. And that limit your risk in your project, and that might at some point increase your credibility through that of the partner, so through us. So you have an external perspective, an external team of experts, adding some credibility to your project. And finally, we can accelerate your development and innovation by having the resource you need.
Thank you so much, Hugo, for that great presentation. It was really interesting to see how the simulation technique works in practice. Now, we'll move on to the Q&A session. If you haven't already, feel free to type your question into the Q&A box. We'll do our best to answer as many as we can. So let's start with the first question we received, Hugo. The first question is, the helmet does not appear in the model. Did you take it into account in the simulation?
Yes, it's true. Good catch. I didn't mention it in the presentation. Yes, in fact, representing the helmet by finite elements physically in the model was not necessary in that case, since it's not touching anything. It's just added mass. So yes, we included the helmet, but we included the effect of the mass on the head. So we added the mass directly on the head fem, and we didn't represent it explicitly the helmet, but we added the effect of the helmet in the simulation.
Good. Thanks for the answer. The second question is muscle active contraction represent?
Muscle active contraction. At some point in the project, when we began using the thumbs, we wondered if active muscle contraction can play an effect in the simulation results. So yes, we thought about it, but we did some sensitivity analysis, because thumbs allowed us to do so. So we did some sensitivity analysis and realized that active muscle contraction is nothing compared to the other loads at play here. So the number of G's you can see at the ejection is way over what muscles can add. So the active contraction is not significant in that case.
Makes sense. The other question is, how precise are the vertebral compression results from the simulation?
Vertebral compression results. So I would say that for the specific case we represented, if you had a pilot exactly identical to the finite limit model that we use, the vertebral compression is really precise. But in order for it to be precise, you have to have the same size of the body, the same material properties that we use. So they are really precise. So what we inputted in the model, but all the material properties, the size of the body, and all that contain a lot of variability from one individual to the other. So they are very precise, but we have to manage a wide variation of the results based on the wide variation of bodies you can find. So these are as precise as it can be. Let's say it that way.
Great. That was a great question. I have two questions left. Thanks for asking your question. The other one is, does your client face ejection from its plane in the past? Does the new seat improvement have been integrated to the fighters?
Okay, that's an interesting question. So yes, our client experienced some ejection in the past, and that's where the requirement for this project comes from. So there was really an urgency to deal with it in order to make to reduce the risk for the actual pilots of these planes. And is the other part of the question, where the improvement integrated in the fighter? So at the point we are talking, the first crushable and the engineered foam and the crushable have been added because it was really fast and to add them, and we are working on integrating the remaining solutions, so the belt retractors and the orthoses.
Exactly. Thanks. I think it's the last question now. Does the bio-fidelic model can be positioned? Does the model need to be adapted on the shape and the size of the seats?
Okay, so the bio-fidelic model that we use, the thumbs, can be positioned. There are a few ways that we can use to position it, but it's really challenging to preserve the anatomical accuracy of the model and to preserve how the different articulations are going to react. So for the position that is the case. For the shape and size of the thumbs itself, we used different version of the models available for the sensitivity studies. It could be possible to modify the mesh itself and to recreate some other body dimensions, but we didn't go into that for now. We ensured that our solutions were robust, and our conclusions were accounting for some variabilities, but we didn't modify as much the mesh of the original thumbs right now. So, and for the shape and size of the seat, yes, the seat can be configured differently. For example, if you have smaller, taller or smaller pilots, so they can adjust the seat according to their size. And we have the finite element model making it possible. So we have a finite element model that we can configure for the exact size of the pilot to be able to simulate it in different configurations.
Thank you, Hugo. It was the last question, so thank you all for your great question. It was very interesting to answer that. We hope you found the session helpful and informative. Before we wrap up, we kindly ask you to take a moment to fill out our short survey. It's just 3 quick questions, and your feedback will really help us to improve our future webinars. Thank you again for joining us today, and we hope to see you at a future session.
Thank you, Guillaume.